So we were at M, right? So the message, it will assemble the message, start with the address, which is the fake address, and then the destination address, right? And following that, it will wait for the user to start typing the message. So when you type, as long as it's not an enter key, which is this guy, /R, it will be able to get into here and print it out. So you can see when you're typing, you can see it at the same time, okay? So I think you should be able to see this in PuTTY, even though your ISRs are not working, but you still should be able to see when you're typing, it shows up in PuTTY. Because that's just, it's already given, right? If you have all the variables and everything declared correctly, when you are typing, you should be able to see them, okay? And then you press enter, this one is getting this is not getting satisfied anymore. It jumps out from the loop. Okay, and then it puts the now terminator here for the string, and then the checksum, which was computed over here, right? Every time you typed anything, it will be added to this variable checksum. Just keep adding the ASCII code of those letters into this variable. So eventually you got a checksum ready. So you put the now here first, and then the checksum as the very last byte to be sent. And that's it. So then this one will print out the whole. Also, you press R, right? Press enter. It will come to this point and then shows that message entered. So the message entered, which means the message has been stored in that transmit buffer. This guy. Okay, in this way. So basically, when you are typing, the M case is actually assembling all the messages into it, including the commands, the address, and the now terminator, and also the checksum. So press enter, it will be done. Everything will be put into the transmit R buffer. It's ready in the buffer. Okay. So whenever the message is over there, if you don't press S, it won't trigger. The ISR is still going on, but it won't turn on the flag. So when you press S, you can see the first thing is to turn on the flag. So all these are given, right? So this is nothing you need to code up over here. So when you turn it on, this flag will be on, will be true. All right. So in your, and then it jumps to this. Well, it is true, right? So it's waiting there. It's waiting there. So in your ISR, you can imagine the ISR is always on. It's keep going to the ISR, and it checks the flag. Whenever the flag is true, it will start getting into all the states, right? So going from the first state, the idle, to the very last state, and in the very last state, you're gonna turn off that flag. So this one is waiting for here for everything getting transmitted. So this won't be satisfied anymore. It jumps out from it. Okay, so it's basically you press S, you do this, and boom, waiting here. It's waiting. Okay, so the ISR detects the flag and keep doing the transmission, getting all these messages sent out in the air, and then the receiving buffer will receive it, but that's something else we're going to look at later. But it will be transmitted, and at the end of the state, the very last state should turn it off. So whenever all the messages are done, right, it should come back. When it comes back to here, this is not getting satisfied anymore. It jumps out and print transmitted. So it's done. Okay? And transmitted, you want to let the user know what has been transmitted. So it prints out this. See this one? It's a little interesting. It's in C. If you haven't taken C++, here just let you know. All right? There are not too many things you need to know, but this is another thing you need to know. So if I'm trying to print out the name of an array, it's actually using that name of the array as a pointer. The pointer is like pointing to the first element of the array. Okay, don't worry about that if you don't understand what pointer is. So the name of the array is actually a pointer of pointing to the first element of the array. Okay? It prints out, if you just print out the name of the array, it prints out the first element. However, because it's a string and terminated by the now terminator, so if you do this pointer +2, it's actually moving that pointer to the second, not the second, actually the third, because 0, 1, 2, right? It's the third element of the array. It's going to print out that one first. Why want to print out that one first? Because we are printing out the message starting from number 2, index number 2. Okay? If you print out this byte over here, and it will directly detect the whole string and print out every single thing in the message buffer and terminate it by this now, and it will directly print out everything. You don't have to have an index and print out one by one, have an index increment every time. It's just something embedded into the C language. Okay, it's gonna do that for you. Does that make sense? So I only need to print out transmit buffer, IR buffer +2, which is the first element over here pointing to here, and it will directly print out all the bytes in the string and end it by this character over here. So that's why this is useful. That's why we want to plug in this little character over here. This byte, I'm sorry, this byte over here. So that is why when this is getting executed, right? When this is getting executed, it will directly print out the message you just typed in. It will directly print out the message you typed in. You don't have to print out one by one. It's directly everything in the string. Okay? And then followed by checksum and addresses, which are just constants. This is not constant, but they're just numbers. 3 more bytes following that. Okay, so it's showing whenever you press S, it transmits first because this triggers the ISR. Turn on the flag in the ISR is transmit first. Whenever the transmission is done, it prints out what has been transmitted by these following lines. And then you press after that you press R, right? You press R. If the receiving new message is true, it's going to print out everything over here. Otherwise, it won't. Okay. So it's trying to detect this byte over here, and every time it prints it find out this byte and it add it to the receive checksum. So for error checking purposes. So the receiving is pretty simple. It's given. You don't have to change anything. Just directly use it. Okay. You can see all the rest of the receiving code is super similar. Just printing out everything in the receiving buffer, and the receiving buffer is being filled up in the receiving interrupt, which is given, mostly given. Okay. So here's a template. Okay, template. So your major task is to fill up this transmission ISR. But the receiving ISR is mostly given. Only this little case over here is not given. I think it's reasonable. Okay, it's really challenging but reasonable. So I'm gonna start drawing the state diagram for all these states. So during that time, I will show you most of the code for each state, but maybe not every single thing. You may need to add one more line somewhere here or there. But we'll cover pretty much 80% of the code. I will just handwrite on the paper. And well, I'm drawing the state diagram for you guys, okay? To make it even easier. So let's start working on that. So you can see these are some of the static variables being declared, right? And this is the state variable, and every time it goes into idle, but the thing is, if this flag is not on, it won't do anything, it will just directly break. So ISR is always on, right? But only when this flag is true, it will do something and start doing all these transitions between states. Okay? So whenever this, so you see, what are the states we have? You don't have to have 4 states. You can have more. You can have less. I mean, less will probably a bit, trickier. But You can have more, definitely can have more. So based on these 4 states, I think for the first one, whenever the transmission is true, right? So the first thing we want to do is go to the next state. So we don't want to stay at idle anymore. So next time it enters it, we'll go to the next state. Why? Because the idle state is not doing anything. But the start bit should be the first thing you want to do, right? Because the IR is being put into the envelope, which is 1200 bits, 2400 bits per second. And it starts with the start bit, which is put down to 0, okay? So if we draw the state diagram, start with TX idle. So whenever it enters that, so within that if statement, because it will start doing the transmission next time, and you don't want to keep resetting the index to 0 in the future, so it's better to put the index to 0 over here. Does that make sense? So let's do this. Transmit, what's the name of the variable? Let's just keep it the same, okay? Transmit buffer index. Give a 0 to it. All right, and then T, it's a timer, 3 IR, ISR, state should be the next. What's the next state? Start bit, TX. So these are within the if statement, right? And you don't have to do anything else because it's idle state. You're not actually doing anything, right? And it has to be true. So when transmit start, okay, so go to the next state, which is TX. Start bit. So in the start bit, okay? So the first thing is, because next time, so this is the first time it enters the if statement and it detects the new state, so assign a new state to it, and then it breaks after it, right? Breaks after it, and then eventually the next time it interrupts, it will detect a new state, will directly enter here, and you are so you should start pulling it down. So how do you pull it down to 0 for the UART? Set to 1. So turn on the PWM. Okay, first turn on PWM. Do we need to set a timer over here? No, that's the ISR, right? ISR will do it for you. It's the timer 3 control. Okay, turn on it, turn it on. And also, what else you want to do? So probably the mask. Initialize the mask. 0B, 00, 7 zeros and 1 1, right? Initialize the mask. Why? Because I mean, you initialize the mask over here, so next time it gets in the next state for the data bits, it won't always reassign this initial value to mask anymore, right? It will keep going. So you want to initialize it over here. But that may not be super required. You can also control it for the declaration over here because all these are static variables. So it should retain its value every time it enters. But just in case, okay, you can try if you want. But I thought it will try it. Because we're running out of time. All right, something you want to try, okay? If you like to. What else? Data. You want to give the data to the ladder, right? So ladder is something you want to transmit. Ladder is something. It should be with the index, right? So it should be index and array. So it should be like transmit our buffer bracket index. Because every time it changes, right? Every time it changes, it just initialize it over here. What else? This could be a quiz question. What else? It's really simple, actually. What else? Next state. Oh, timer. ISR. State equals what? Look at the state. What's the next state? Data bits. Data bits. All right. So this covers mostly everything, but if there's anything's missing, you will be able to debug it, right? Since that's the expectation in this class. Debug, troubleshooting, software and hardware issues independently, okay? Go to the next state. Is there a condition to go to the next state? Is there a condition on the top of the arrow here? Go to the next state? No. This is being executed once. Once it's done, next time it interrupts, it should go to the next state. There's just only one start bit. Okay, so what's the next state? TX. Okay, what should we do over here? That's a major one. Remember the mask shifting thing? Okay, we have examples on the website, the mask shifting thing. So you have to have an if statement, look at the bits, the data. So I just write it here since we have examples on the website. All right, there are all examples from task 1 and 2, right? Is there a condition to move to the next state? Remember what's the condition? If when mask becomes what? When mask becomes 0, because that little single one here is being shifted to the left every time, right? Every time. And whenever this one is gone, being shifted out from the left, which means all the bytes are sent. So every time it detects the LSB and the second one until the MSB, and then the next time it's shifted out, so mask becomes 0, and which means all the data are sent, all the bits are sent. Okay? So how many bits are sending during this state? 8. Okay? 8. Then the next one will be TX stop bit. What's the first thing you want to do? Stop bit is pulling up, right? It's pulling up. So it's like like this, okay? Like this. So stop bit is pulling up. So first thing you have to do, because all the bytes are done, the next time it enters the ISR, it goes to this state. So the first thing you want to do is turn PWM off. First thing, just turn it off. That's just one liner, remember? That COM5B or something, right? Turn it off. So this one getting put up. You have to send this message, otherwise this is not stopping, right? So send this message. So whenever this message is getting received at the receiver, it will trigger so the receiver side will know that the whole message has been sent. Right? Have to put it up. So put it up first, and you have to look at the if statement, because from here you have to make a decision if you want to jump back to idle or to start bits, right? So what are the different conditions? You still have the current index here, right? Still have the current index.
Your message is done.
If the message is done, so what do you know? How do you know the message is done, right?
Is that the count?
Mm-hmm.
Is that
The count. The count. It could be. You could use a count, but no, because you don't know how many bytes are in the message, but you can definitely count it, right? So you have to set a counter.
The sum, the check sum.
Yeah, the checksum.
Can you use that? And if the checksum of what you sent versus the checksum of the total is
Yes, you can check this as well, but I think so you can, right? But what about this guy? Because you are always plugging this null terminator in the message, so you can see if the current message is at here or not. If it's at here, what you want to do? Go to idle or go to start? No, because you still have another byte to be sent, right? So the thing is, if the current one to be sent is this guy, what you want to do is go to the start bit, because you want to go to start bit to put it down again to start a new byte, which is checksum, the last byte, and you want to set up a flag, telling that next time it comes back here, it's already at this checksum state. So the next state should be idle. Let's write it down. So if this is detected, you want to go to TX to read checksum. That's the last byte to read. Else, if so, then the thing is, if this is the current thing that just got sent, right? You want to go to this one as the next one. You want to go to the start bit so you can send checksum as the next one, but also within this if statement, at the very last thing, you want to add a line. So you can see I have a example over here. You need to set a flag, which is this one. All right, it's just a little flag. So what you want to do is to use this flag and put a TX checksum to be true. All right, so the next time it enters here, definitely this won't be the current character anymore, because you are always adding a 1 to the index at the end. All right, so I'll let you guys handle that index by yourself, but it's pretty easy to figure out. Okay, so else if you are looking at a condition, which is TX checksum, which is this flag you just set up from the previous cycle. If this is true, right? Else, if this is true, you want to do something. What are the things you need to do over here?
Our next state be idle.
Set checksum, TX checksum to false.
Yes. So whenever it's true, put it back to false. So next time it's not coming to here anymore. And also put it back to idle. All right? Because you're done. Because checksum is true and that reaches the stop bit state, which means already has gone through all the states to send the checksum byte. So which means if it reaches here, the checksum byte is gone. It's already sent. All right? So you want to set the next state to be idle. Timer 3 ISR state to be what? To be idle, right? It's TX idle, but just let you know it's idle. And also checksum. No. Be false. Did we cover all the cases? If it's the terminator, we do this. If it's a checksum, we do this. Is this the only thing we have, or is this the only things we have in the message? No, so we got an else, right? So else actually covers the normal cases, normal situations, normal messages. So what you want to do in else? It's just general cases, right? You figure out the tough ones first, and eventually the last one's the easiest one. So what you want to do with the with that? If it's just a general one, whenever it reaches here, I already put it up, which means that byte is already sent. Okay? And it's not null, it's not checksum, it's just something, it's just regular ones, right? And I'm ready for the next one. So what you want to do here? Stay to where? To where? So that byte is done, right? I need to start a new byte. And what's the first thing for the new byte? The start bit. You need to put it down. So every single byte need to be wrapped by the start and stop bits, right? So this one should be T timer 3 SR state to be TX. All right. So if we consider this whole thing here is one block, right? So no matter after which one, it could be this case, this case, this case. So no matter which one, we should do one thing. And what is that thing? Because every time you see here, that's transmit IR, probably the name is wrong, but you know, buffer index, right? Okay, see? Idle, boom, next state. Initialize all the things and give this index this location of the buffer to the ladder, and then the ladder stores that byte, right? And then I start sending that byte bit by bit over here, and then it comes down here. So whenever it comes back, did you see some issues? What else you want to do? See here, idle, change the state, didn't do anything else. Initialize the index, right? Initialize index. It's starting from byte 1, which is the like fake source address, and moves to the start bit. Okay? And initialize, mask, doing this. Okay. The first one, that's the first, first byte in the message, and move to the next state. So I'm doing the mask shifting thing to shift one by one. So I'm sending out bit by bit in the byte, and then come to the stop bit, put it up, and all the checking the conditions. If it's a null, if it's a checksum, if it's a regular case, that's what I want to do. And then comes back. What else? The next byte, right? So you want to do what? Increment the index. So until here, right, you change the index, but otherwise, all before, there are still that current index. just let you know, it's a comment over here because, you know, when you are doing the checksum conditions, you can consider, oh, which address I'm at, which index I'm at right now. So you should know that it's only being incremented at the bottom of the stop bit state. Okay. I think it's a reasonable solutions being given to you guys, and hopefully you guys can figure this out. Okay. Any questions on this? So, I think we should start working on your PCB issues. If you have questions, you can ask me regarding how to install it and how to use it as well. If you already installed it, already in the process of designing a schematic. If you have issues with the device, with the laptop, let me know. There are some laptops, I got new ones for the quantum grant for high schoolers. I can let you use it temporarily, but eventually you still have to get your own laptop, either from the IT or from somewhere else, hopefully. Okay. If you still really have issues, you know, feel free to check out one for me. I just have to use it during the workshops, which is maybe only a few days this and next week, and maybe another week in December, and that's it. So you could use it. You could use it.
Do we have to do Eagle or can we do Fusion?
Fusion is fine. Yeah, just let you guys know. The desktops have Fusion 360. Interface is very similar. It's basically just someone plug in the Eagle software into Fusion 360. It's the same software. Only several of the windows and menus are slightly different, but the major things are the same. And also something else to let you know. I'm not expecting your board is significantly larger than our Skyboard. The free Eagle version has a restriction on the size of the board. I think it's 10 centimeter by 10 centimeter as a limitation. So if you want to make a bigger board, you still have to use Fusion 360. So you can, you know, always design. If you are more comfortable with Eagle, you can design your board with the major components in Eagle, and then modify it in Fusion 360 if that's a better way to do it. Because Fusion 360 doesn't have the limitation on the size. All right, and the cost of the board is not significantly higher than if you have a bigger board. It's usually, you know, if it's not $2, something like $5. If a bigger one, maybe $10 for each, it's still fine. I can afford it. It's just the shipping and tax is too expensive. But you know, we'll be able to fabricate all the board for you guys. What's up?
If you have no experience in Eagle or Fusion, which one do you recommend using?
The old tutorials are on Eagle, so I recommend Eagle probably. Yeah. Yeah. There's another one called KiCad. Someone used it. But since Eagle is being integrated into Fusion 360, so I think it's getting more support from the engineers over there. Yeah, it's a very decent tool to use actually. Altium, which is another one, I'm not sure if it's free. It's probably free for students, but you know, if you're out of school, it won't be free anymore. Yeah.
Are we still recreating the whole Skyboard schematic?
Yeah, so I'm thinking you could probably make a smaller one. If you know what you are going to use, you can always change it. Let's say, so the main goal is here is to practice on the PCB skills, right? So if you don't want to lay out the whole thing, for example, you decide to use IC card module, even though we haven't learned it, right? So you need to find out the SD card module, which is over here, and the main part, which is the main microcontroller, is here. And this chip is a USB to UART converter, that serial chip, and we don't need it. So all these components over here can be removed. And we're still using USB to power it up because that's a requirement of the project. So we're still using the same cable to power it up. So you need to keep this port over here and use 5 volts just the power supply, not the communication or data for data purposes. So still keep this 5 volts, and you have this microcontroller, and you have the SD card. For example, you are trying to log your your voice, right? So you can use the microphone, which is this part, and the SD card, right? If you just want to play a music and have a RGB light effects, to show the music when the music bumps and detects the frequency and show some lights over there, which is the speaker, the audio amplifier, which is this guy, audio amplifier, and the speaker module, right? Speaker module is it's just audio amplifier, right? And also the LEDs, RGB LEDs. Remember, you have to integrate two different modules from the Skyboard. We have microphone, we have RGB, we have audio amplifier, we have this is a low pass filter being used for the DDS. So that's another really important technique you guys should know actually. We're just running out of time. I don't think we can still do it. It's using different frequencies to generate analog signals, like the general function generators in the lab, right? How they generate all these analog signals, right? So they used DDS, directed digital synthesis, and so this is being used for quantum computers interfaces as well recently. So it's a really important technique to learn. If you get into some of the national labs, and they're asking to generate different waveforms just using IPGAs. And that's the technique you want to use. So this is for the DDS part, and we have IR, right? IR modules of the SD card. Okay, so all these different modules. You have to pick up 2 of them to put on the board. If you have questions, you can let me know. But for the first assignment, right? For the first set of assignments, which is a PCB one, I wouldn't ask you to get a functioning board actually. Because the goal is to just practice your PCB skills, so you are ready for your design. So you can see the due dates are pretty close. I think I moved this one to Sunday. Okay, so the first one is Sunday, and it's still Monday. Okay, and layouts. So follow this one will keep you. So learn how to have a good practice on your PCB design. I think it's important. You just still have to finish the layout over here. But for the 1.4, task 1.4, right? You don't have to finish the whole board. Just pick up 2 modules that you would like to use. Even though you could change it in the future, but just pick up 2 of them, right? Pick up 2 of the modules. And you don't have to integrate anything over here to it. And you just need a USB port, find out the 5 volts, and do a power supply. Even though there are some of the connections are incorrect, we will always be able to fix it in the future. Okay, so you have after this assignment, you will be able to have an initial design of your PCB. Well, at least you have the microcontroller on it already, right? So the next steps are, after we covered all these other tutorials, we know how to learn use ADCs and the IC cards. That's the last 2 tutorials we are going to have. You can make a decision if you want to change or not. Okay. But you can see, grab a microcontroller schematic, the symbol from it's available. You are not doing this by yourself. Okay. It's basically just a drag and drop. This is available in the library. If it's not, find it from somewhere else. You're not doing this by yourself. So drag and drop your schematic and figure out power supplies. We can take a look at this right now actually. So every time you start a design, you want to start with the power supply. Keep in mind, every single time. Because you need to know the power consumption of the circuit, and usually all these microcontroller devices with the LEDs and everything, it's going to be no more than 0.5 amps. It's pretty low power device. So usually the USB from your laptop, from the computer, will be sufficient. Okay, provide sufficient amount of current for your circuit. Or if you want to use a regulator, which is a lot of times as a product, we usually encourage students to use a battery power supply with a voltage regulator on it. That's another very good practice in the future. I mean, a lot of times the interviews will ask you the questions. I mean, what's the voltage? How to supply the voltage, right? So this is a fundamental thing you guys need to learn actually. but for this time, you can, during the interview, whenever they're asking for you any projects you have done, right? Talk about the projects. So you can tell them, I just use the USB to power up my circuit, which is fine. So USBs are always 5 volts, keep in mind. It's always 5 volts. Okay? So if you have a circuit component which requires 3.3 volts, you will need a regulator on it. But we are not, I don't think we need a regulator here. If you use SD cards, there might be a regulator inside that voltage shifter on the top. But this is something we'll talk about later, okay? So we're not getting there yet. So let's look at the power supply first. That's a USB port. You can see there are 4 wires. And D plus D minus is a differential signal input. That's the signal. So you don't need the signal line because you are not uploading or downloading anything to your microcontroller. It's not programmable. Okay? It's not programmable. So you just need this one, which is the power supply. You can see it has a fuse on it. It's a fuse. And it supplies the 5 volts. And then the ground. That's it. Just 2 terminals on the USB port are being used. One is the 5 volts power supply, one is the ground. So leave these two lines blank. Don't use it. Just leave it there. So this 5 volts comes to a lot of different places. You can see. So the name of this terminal is called supply 1 underscore plus 5 volts. We'll make it easier in the future for the next version. But now it's called supply 1 underscore 5 volts. Remember that, okay? And then you look at the microcontroller. I want to look at the microcontroller, see how this is getting powered up. All right, how this is getting powered up. You want to look at the power. It's supply 1 underscore 5 volts. Okay, seems like that voltage is directly being used over here. Supply 1 5 volts, right? The same name? Yeah, supply 1 underscore 5 volts. Same name. So this is directly shorted to the power pin of the microcontroller. And there's no regulator on it. Why? Because the USB cable, which is connected to the desktop, and your desktop, whatever the USB chip in there, they must have some sort of regulators, right, to stabilize it. So you don't have to worry about that 5 volts. You can trust that 5 volts stable. So that powers up your whole thing over here, and all these capacitors are just filters. Get rid of the noises from different frequencies. They're not super important since we trust that 5 volts, but you add it, it's gonna remove some of the surges. And this is a inductor. Remember, the inductor is gonna reject what? AC or DC inductor? AC. So AC signals by chance comes through this capacitor from the ground will be rejected by this guy. Okay, or you can say maybe any AC surges, because the power supply, sometimes the power supply is getting affected by the signals, right? If it's not stable at the point, and this will reject it, so it's not being sent to AVC. So why we worry about AVC here? Because AVC is a reference voltage being used for the ADCs, and usually you want to keep the resolution and sensitivity or quality of the ADC conversions, right? So get rid of a lot of noises from the ground, and that is why you are shorting this one to the inductor, right? So you can isolate this stage from this power supply stage for the ADC's reference voltage. And you don't have to do anything over here. I'm not going to put this kind of question on the quiz, right? So it just follow. If you see a capacitor here, just put a capacitor over there. Not too bad, right? Okay. And the clock, okay, so see the Arduino products, why they are not super popular in the industry. They're expensive, and they don't have a lot of peripherals on the chip, and they have external oscillators. So you can see a lot of like the PIC ones, even though they when you program it gives a lot of pain, but so the PIC one I used is a 16-bit microcontroller with 2 to 3 UARTs on it. And it's only $1, and for this one $17, and even for the Arduino Uno one, the very beginner's version, I think it only has 1 UART. Right? If it only has 1 UART, we put a UART into the USB and trying to look at the serial monitor, we won't be able to perform any IR transmission, So that's why we decided not to use that Uno board. but it's okay as an educational thing. A product is fine. So this one, $17, all right, has a external oscillator, 16 megahertz. That's the little tiny thing. If you look at the board, you can see that little tiny shiny one, right? Silver colored little tiny thing. That's the oscillator with 3 pins. You have soldered it, right, by yourself. That's the oscillator. Has the internal capacitors. That's the oscillator itself and capacitors. So for the big one, you also see a bigger oscillator. It's a bigger crystal. It's for the USB to UART converter, and you can see it's over here. It doesn't have an internal capacitor, so I have to connect the 2 capacitors next to it. This is increasing your footprint of the whole board significantly. But we are not using this chip, so we don't have to worry about this. So you want to follow a better practice. It's a better oscillator to use, and we did use it for the skyboard, and we use the same thing for the skyboard. So just to place it, this is available in the library. Just place it in your schematic and make the connections. Very simple. Boom, boom, boom. 3 connections. So ground in the middle and have 2 connectors to the 2 inputs. It's a differential inputs for the oscillator, for the clock in, right? Clock. See? Power, oscillator. Anything else being shorted, being connected to the microcontroller? Not really. Have 100 pins. You can see most of them are empty. And you can make them available if you want to be nice for the users in the future. If you are the user, you don't have to worry about that. So have all the pins available. If you don't want to make them available, it's fine, right? You just make the ones you care about, make them available. Have a header pin on it, so you can always have a jumping wire, connect to that pin. If you don't make them available, there will be a little tiny surface mount pin next to the chip, and you won't be able to access to it. So you can see all these pins are not really used, only several of them. You can see, so we already went through all these tutorials for what? For the speakers, right? So speakers for the IR, for the RGBs, you already know what are the pins being used for these parts. Remember the PL4, PE5, remember these ones? Or the jumpers, pin 14, pin 19, pin 44, all these kind of things. So these are being used for certain modules. If you are more comfortable of using these pins, since you know it works for the experiments, for the tutorials, you can keep using these pins. I'm not going to ask you guys to change pins. You can keep use the same pins. Okay? Shows up in the tutorial. You can just keep using the same pins. And you identify the pins from the schematic over here, and you'll find out, all right, so these are the modules I need. For example, for the audio amplifier, you can tell, oh, so so this name pre here, pre is shorted to where? To a header, which is somewhere. Oh, you can find it. Okay, somewhere it's shorted to here. Okay, if you're not using this low pass filter, it's not required. You don't have to use it for the speaker. Just find out. Just look at the hardware connection that worked for you for your assignment. Right? That one was already verified. You know it works. Look at the connections you have, and go back to the schematic and find out what are the modules are involved in that tutorial, in that working, the functioning work you did. Okay, and then just put them on the PCB. After you finish this, the power supply, right? Just pick up the ones you want to use, whatever design you want to have, put them on the boards for the task 1's assignments. And again, they are not the final design for your board. You can always change it, but just pick up 2 of them that will likely be on your board in the future, and then turn it in by Friday next week. All right. Any questions? I think so.
In task 1.1,
Yeah.
it says to follow the lab instruction. How do you navigate there from the link, the lab instruction link at the top?
Oh, you don't have to go to there.
You just go through the pictures.
Yeah, the pictures will be enough.
Okay, that
Will
was
be
just
good
like
enough.
we want to know where it came from.
Yeah.
Okay.
So I think he changed it to somewhere else. Yeah. Yeah, this should be good enough.
If we wanted to use a battery, would we need?
Yeah, if you need a battery, you need to use regulators. So what kind of battery you want to use?
Oh, I was just thinking.
Yeah, you can put in the proposal.
Okay.
Yeah, we're not here on Monday, but we talked about the proposal. Proposal is another assignment, which is here, task 2.1, right?
Yeah.
Yeah, battery is fine, but for the for task 1, you don't have to worry about that.
Okay.
You just need to learn how to use the PCB software. And for task 2, you put whatever you think into the proposal, and I will give you feedback. So I'll have all this experience. I will let you know if that will work or not. Okay. If you use battery, depending on the voltages and different cells, I will let you know what kind of regulators you want to use for the board. Easy.
Do you know how difficult it would be to add a charging circuit?
No, easy. There are 16 circuits you can use. We have one examples for this.
Okay.
Exciting, right? Have a USB charging. And, yeah. Anything else? All right, that's it today.